Omar, and I'm gonna be walking you through the main part of our program. So this program is designed to add an echo effect to an input .wav file and save the output as a new WAV file. So starting off, our program expects some command line arguments. Here we have a D command line argument, which is specifying the delay, and then V the volume, which we're gonna scale our samples by. Uh, so we parse the command line arguments and we use get_opt to parse these command line arguments. And then we have case switch statements to ensure that we have the proper arguments given to our program. And then here we just check where if we have been given an incorrect amount of command line arguments. So it's just like a sanity check. Now we're ready to get our file names. So here we'll open the input file in read mode, and if we encounter an error, we will print that to the terminal. Likewise, we open our output file, check if that and check if we get any errors with that. Um, and now after that, then we're ready to copy the header. So WAV files have a standard header at the beginning, and this describes the file's format and properties. So we read it from the input file, and we write it unchanged to the output file. This step is essential because it contains information like sample rate and bit depth, which should remain consistent between the input and output files. And after that, we are ready to add the echo, and we will call the add echo function.
Hello, my name is Ilyas Omardian, and today I'll be explaining my contribution to the team and going over fixed header, and also I'll be doing the testing of our final project. So I'll start with the fixed header. Um, in add echo, not that we're technically creating a new WAV file which adds echo to any WAV file that we want based on a delay and volume that we have in mind. So, and in .wav files, the first 44 bytes are always descriptions of basically what the WAV file is about, and basically it goes over the details of the file. And since we're adding, like we're changing these bytes of the original file to add the echoes, we need to change these first 44, some of these first 44 initial bytes as well. And one of them is at by number 4, and this is basically what we're doing. First, we're reading from our original file, and we are sending it to the header, and then here we're uh, assigning it, and we're checking if we multiply it by 2, if it's greater than the size that can be represented in 4 bytes. Uh, we return an error because, well, that's going to cause an overflow, and we also do the same for the byte 40.
Hey guys, my name is Harsimar, and in this video, I'm going to demonstrate the code for add echo, which is basically the main code for our program. So we have our code right here, but for the purposes of this demonstration, I'm going to explain the code using my iPad so that I can better explain it using an example. So here we have the code right here. So basically, what happens is, first of all, we create an echo buffer, which creates space on the heap so that we can store our samples. And this basically keeps the most recent delay number of samples, which was described in the assignment. So here we are using this example, which was described in the assignment with delay equals to 3, volume equals to 2. So basically coming back to our code, we have an index counter, which basically keeps track of the all the samples that we are reading from over here. So we start our code by reading sample by sample. So we read one item at a time, and we calculate the scaled sample by dividing the value of the sample by the volume that was given, which in this case is 2. And so let's say if the index was 0 initially and delay is 3. So basically, since index is less than delay, so what happens in our code is we write this sample directly to the output file. And similar things happen for index 0, 1, and 2, which are basically less than the delay. So which is this else statement. We write the samples directly to the output file. Also in the echo buffer, at those indices 0, 1, and 2, we store their scaled samples and we keep track of the index. So now once we reach the index 3, which is greater than equals to D over here, what we do is we take this value and we add the echo buffer 0 value, echo buffer 0th index, which is basically 1. So echo buffer initially stored the values 1, 1, and 1, which is basically the scaled down version of these values. So now once we reach the index 3, we add 1 from over here, and that is our new value 3, and we write that to the output file right over here. So this is sample plus echo buffer 0. We write that to the output file. Also, since now we are at this index and we only have space for 3 elements in the echo buffer, so we need to create some space for this element. So what happens is we shift all the elements towards the left by 1. So this gets removed, this element gets shifted here, and this element gets shifted here. So now we have space for the third index in the echo buffer. So basically, this part of the code shifts everything towards the left by 1 unit, and then we add the new scaled sample in the echo buffer. And this keeps going on basically till the end. But towards the end, by the calculation, we will notice that the echoed versions of these three samples were not written to the output file. So we take the echo buffers elements and add them over here. So these scaled down versions of these are twos. In this example, the 0 samples were not added because the delay was less than the total number of samples, which were 20. Delay was 3, so this was less than the original samples, so no 0 samples were added. And this part of the code basically handles the writing whatever is remaining in the echo buffer, which has not been echoed part has not been written to the output file. We add it right over here. And now for the 0 samples part, I will give an example. So let's say we have these samples 2 to 4 and delay is 5. So what happens is initially the initial part of the code will write these original samples to the output file just like that. And then the 0 samples will calculate the difference, whatever samples are remaining. So these are 3 samples, delay is 5. So we need to write 2 samples of 0 to the output file, which will be handled by this part of the code. And then in the end, what this part of the code will do is it will write the scale down versions. So 1, 1, and 2, like if volume was 2, so scale down versions of these to the output file. As for the if else statement here, basically what happens is it depends if which one is bigger. So if the delay is bigger, we write the number of items of like the original samples number from the echo buffer to the output file. But if original samples is smaller, so original samples is greater, then in that case we write delay number of items from the echo buffer to the output file. And the reason for that is basically we know that if D is greater than the original samples, then the echo buffer will basically contain the original number of samples, but their scaled down version. So we only need to write their scaled down versions to the output file. But in the case when the original samples is greater than the delay, which was the first example, we know that the in the end the echo buffer will only contain delay number of samples which have not yet been echoed. So that statement will write these to the output file. So that's why we have two if-else statements for these two cases.
So now we'll be testing the program using one of the lab machines. Note that we SSH into it, and we're running the GCC command using wall and werr to show all the warnings and all the errors. Note that we have a folder here called samples, and it contains all the audio files that we'll be doing the tests on. Our first test is going to be on is going to have the values of delay of 60,000 and volume of 1, and it's going to be on door.wav. Note that this is going to be sent to test.wav, and this test.wav was created. Now we'll be testing if the output file is equal to what we're supposed to get, and note that we do this using the CMP, and if CMP returns nothing, that means that the files are the same exact thing. Our next test is going to have a delay of 3 and volume of 2, and it's going to be called on short.wav, and then again we're going to be sending it into test.wav. Now you can see the list of files, and you can see that the test.wav has a size of 90 bytes. Now we're going to be showing the bytes of our short.wav using the od command, and now we're calling the od command on our test.wav, and you can see the changes between the files. Now we're gonna again be using the CMP. Note that the CMP returns nothing if the files are the same exact thing. Note that we downloaded the short answer that was provided in the website. Our next test is gonna have a delay of 25 and volume of 2. Note that our short file has only 20 samples in it, and this is considered an edge case because our delay is more than our original sample in our short file. And we again send it to the test.wav, and now you can see the bytes in test.wav. Note that after the 20th byte we have 5 zeros as wanted, and the next 20 bytes are scaled down versions of the original file. The next test case is going to be on mt-d and mt-v, and we handled this case using the default values, which delay is 8000 and volume of 4. Note that using the od command will show that 8000 bytes were added to the test.wav. Our next test case is going to be also another edge case where user sends in random arguments, and again the way we handle it, we just use the original default values of 8000 and 4. And again, we're going to be testing it on short.wav and then sending it into test.wav. Note that again, using the od command, you can see that the bytes have changed, and we have a star here which shows that the bytes are so big that can't be printed out, so we have 8000 bytes. Our next test case is going to be passing a negative d value and a volume of 0. Note that in either of these cases being true, we use the default parameters again. And using the od command, you can see that the previous test.wav with the newly created have the same exact bytes. And our last test case is going to be not having enough arguments and user not providing enough arguments, and then we're going to show an error and the program does not crash.
Hello, it's Omar again, and now I want to touch upon some of the challenges and the issues we face as a team. So one of the first issues that we encountered was when we were reading the assignment instructions to add the echo to the voice sample to the WAV files. So we had a few issues with the instructions. They seemed pretty straightforward, like don't load the entire sound file into memory due to their size and whatnot. However, we kept on having questions like, what is an echo buffer? How does an echo buffer work? How do we implement this? How do we manage the sample delays? What are sample delays? So for this, we had to come up as a team and learn about how .wav files work, and even the instructions skipped over like how these files work, like the headers, the data segments, and how to tweak the data to generate the echo. It was a journey that we all had to work on it together and to sort of understand what is going on, and we explored the world of digital audio processing. And another issue that we had, because we worked on this as a team, even like throughout the whole assignment, we worked on it as a team. Our journey had hurdles, especially when it came to teamwork. So one of the most significant challenges that we faced, and probably the biggest challenge that we faced, was coordinating our efforts, because we all had different schedules, and it was hard to find a time where everyone could meet. We had some of our team members were commuting, some were not, and it was just just a hassle to figure out what time is good that works with everybody. But we learned to make the most from working on it asynchronously, and leaving detailed notes about what the other team member should look into or do when we couldn't meet. And it was a lesson for us in terms of understanding how to effectively communicate, and it showed us that the right approach, even with a dispersed team, could come together to work on these complex challenges.